Hi students, Professor Nugent here. In this video we are going to discuss the second way to transform your data to reflect a nonlinear relationship between a dependent variable and the independent variable. That is to take a logarithmic function of y and or x. When we talk about logarithmic functions in economics, we are almost always talking about the natural log. Alright, so that is log base e of x, e the natural exponent. Alright folks, there are logs with other bases, but in economics we're almost always talking about the natural log. Logarithmic transformations permit modeling relations in percentage terms like elasticities rather than linearly, which is important because a percentage change in x may give a constant percentage change in y over the domain of x, but that may translate to different level changes over the domain in x. Here is why we can reflect changes in x in percentage terms when we take the natural log of x. So if we take the natural log of x plus the change in x minus the natural log of x, so we're looking at what is the change in these variables because of some of the really cool things that you can do with natural log. This is, in essence, the natural log of x plus delta x over x. That's what this equals, and this thing simplifies the natural log of 1 plus delta x over x, which is approximately delta x over x. If we just looked at this in calculus, what is the change in the natural log of x for change in x? So the derivative of the natural log of x with respect to x, it's equal to 1 over x. Whereas looking at the change in x equal to 1, you get that. Alright folks, numerically we can show that given a 1 percentage change in x, then the natural log of x is going to be 1.01, which is about 0.01, right? So that reflects about the 0.01 percentage change. If we look at a 10 percentage change in x, take the natural log of that, and it's about 10. So as you start to look at larger changes in x, then the approximation becomes less accurate. So the natural log approximation is very good for small changes in x. There are 3 log regression specifications, and we have discussed this in class. There is the linear log case, where the data in y is linear, but we take the log transformation in x. There is the log linear case, where we take the log of y, but do not transform x. And then there is the log case, where we take the log of y and we take the log of x, and then our beta 1 is conveniently a elasticity. So the interpretation of the slope coefficient differs in each of these cases. So it's important to verify what is the unit of measurement in these cases, and do you have log transformations, so that you have correct interpretations of your slope coefficients. The interpretation can be found by applying the before and after rule. So you figure out the change in y for a given change in x. And each case has a natural interpretation, and we'll call that it comes down to percentage changes. Let's begin with the first case, the linear log population regression function, where we have y is equal to beta naught plus beta 1 times the natural log of x. And this is the value of y before the change. Then the value of y after the change will be y plus delta y is equal to beta naught plus beta 1 times the natural log of x plus delta x. Now, to identify the change in y, subtract after minus before. And that subtracts y from the left-hand side. And on the right-hand side, we are left with beta 1, and in brackets, natural log of x plus delta x minus natural log. As we showed before, the natural log of x plus delta x minus the natural log is approximately the change in x over x. So the change in y is approximately beta 1 times the change in x over x, and dividing both sides by delta y, multiplying, rather, we can divide and multiply by x over delta x and x over delta x, and we get that beta 1 is approximately equal to the change in y over change in x over x, or a small change in x. Now, if we think about percentage changes in x, because delta x over x is reflected in decimal changes, if we multiply 100 times delta x over x so that we get the percentage change in x, then a 1 percentage point increase in x, which is like multiplying x by 1.01, is then associated with a 0.01 times beta 1 change in y. So this is the key to the interpretation of a regression that looks like this, where y is not log transformed, but x is log transformed. Then a 1 percentage point increase in x that increases natural log of x by 0.01, that is a 0.01 times beta 1 increase in y. Let's look at an example. The first thing that you need to do is to define a new regressor. So you would do something like gen ln income equals log of income. So you define the new regressor, natural log of income. And having generated your new regressor, the model is now linear in natural log of income. So the linear log model can be estimated by OLS. Predicted value of test score is 557.8 plus 36.42 times the natural log of income. So a 1 percentage point increase in income is associated with an increase in test score of 0.036 point on the test, right? That's 0.01 times beta 1, which is 36.42, and that gives us a predicted increase in the test score of 0.36 points for a 1 percentage point increase in income. The standard errors, confidence intervals, R-squared, all the usual tools of regression apply here. And how does this compare to the cubic model? So we can do polynomials, or we can take the log transformation, and you can see that they are pretty close. How might we choose between these two? We might look at adjusted R-squared, so long as we are looking at the same dependent variable, because then we are explaining the same variation. So the model with the higher adjusted R-squared might be a way to choose which model is better at explaining the data. Next, let's look at the log linear population regression function. In this case, we have taken the natural log of y, and x is in its natural form. Now we have in b the value of y before, then we find value of y after for a change in x, subtract the 2, and you get that the change in y over y is approximately equal to beta 1 times the change in x. Solving for beta 1, you get that beta 1 is approximately equal to the change in y over y over change in x for a small change in x. How can we use this? If you multiply 100 times change in y over y, that gives you the percentage change in y. As such, the change in x by 1 unit, so delta x equal to 1, that's associated with 100 times beta 1 percentage change in y. Alright, so a 1 unit increase in x gives a beta 1 increase in ln or a 100 times beta 1 percentage increase in y. In the case that your dependent variable is measured in natural log, but your independent variable is not, then you can use this rule. Let's think carefully. The units of UI and the standard error of regression, they're going to be measured in the same units of the dependent variable that is natural log of y. So we're going to be looking at fractional or proportional deviations. So for example, as the standard error of the regression is 0.2, that means we're measuring the standard error is approximately, is on average 20% away from, or it's on average 20% from the prediction. And this will, and we're going to conclude this video here, and in the next video we are going to continue on with the log model. That's the third way, that's the third variant on log transformations for regression.